This question starts us off with S of t. That's always a position function. Is measured in meters. V0 represents initial velocity. S0 represents initial position. A ball is thrown vertically upward with velocity 30 meters per second off of a building that is 775 meters tall. Use the above position function to address the following prompts. Determine the position function. Okay, well, how do we do this? Well, it's basically just grabbing this function right here, but filling in the V0. What's V0? Well, 30 meters per second. So that becomes 30. That's the 30 right there. And the S0, what's that? That's a 775 because that's how high up the ball was at the start. They were up on some big building, right? You know what I mean? Like if I was to say, oops, that's not a very good building. Just wanted a building like that. Oops, now it's all crooked. It's like a cartoon building. So we have the ground. We have some big building like that. And they're taking a ball. Somebody's up here. I'm going to put a little person. They throw a ball. They throw a ball off the building. The ball goes and hits the ground. All right. So the ball started off at 775 meters of height, and they threw it off. And it came down and hit the ground. Okay, so S0 it says right here, S0 represents the initial position. And so that would be the 775 and the velocity. Oh, they throw it upward. They don't just throw it straight off. They throw it upward and then down. It goes upward, reaches a peak, and then comes down. They throw it upward, and that upward velocity is 30. So that's how we get that first equation. Next, they want the velocity equation. Well, you remember, right? That's the derivative, right? We have the S, and then when you take the derivative, you get S prime, and that's velocity. And then when you take another derivative, S double prime, that's acceleration. So if they want velocity, they want S prime. So I'll go, okay, what's S prime of t? So take this function, take the derivative. The 2 comes down, minus 9.8 t to the 1, subtract 1 from the power. And then the t to the 1 power comes down. 1 times 30 is just 30. Subtract 1 from the power, so that's 0, that's gone. The 775 doesn't have a t, so its derivative is just 0, it's just gone. So there's the velocity equation. And they got that. And now acceleration is another derivative. So this 1 power multiplies down, minus 9.8, subtract 1, it's gone. 0 to 30 is just 0. There it is. That's the acceleration, minus 9.8. And by the way, that really is the acceleration on planet Earth due to gravity. It's minus, because it's pulling everything down, 9.8 meters per second squared. You take physics, you'll learn that is the gravity. In English units, it's 32 feet per second squared. In metric units, it's 9.8 meters per second squared. So that is the true acceleration of planet Earth pulling down on every person and every object all the time, all over the planet. There it is. So if you throw a ball or throw anything up, it's going to be pulled down, accelerated downward by the Earth at negative 9.8 meters per second squared. All right, let's move on. Determine the time. Determine the time required for the ball to reach its maximum height. Okay, so the ball reaches, when does it reach its maximum? So they're going to throw this ball off the building. It's going to go up, 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 reach its. So there's the max right there. What do we know about that max? The ball will stop going up and hang in the air for just a split second, right at the max. The velocity equals 0, which means S prime is 0. That makes sense, right? At the very tip top, when the ball is at the very top of its its maximum spot, top of its arc, the velocity will be zero. The up down, it won't be going up, it won't be going down, it'll be hanging in the air for just the most smallest of a split second. The velocity, the first derivative of position, will be zero. That's how you find the maximum height of anything. So you take that velocity function right here. So you take velocity, which is first derivative, and which is minus 9.8t plus 30, and you set it equal to zero. You set it equal to, I mean, you say, hey, what's going to make that thing zero? What time is going to make that thing zero? So let's solve for it. Subtract 30 from both sides. Gonzo, minus 9.8 t is, oh, I'm just getting scribbly there, minus 30. Okay. And then divide by minus 9.8. And t is, that's going to be around 3, a little over 3. Yeah, 3.061. I'll just assume that's right. 3.061 seconds. So it's going to reach its maximum height just past 3 seconds. Interesting. These are actually true numbers. This is the true gravitational forces. And if a ball really was thrown upwards with an initial velocity of 30 meters per second off the top of a building, it would reach its max height in 3.061 seconds. Okay. And what is that height? So that's how many seconds it takes to get to its highest point. And what is that maximum height? Well, to do that part, better a little space here. There we go. So to do that part, the max height, you got to go back to the S equation because that tells you the position. We're not interested in the velocity now. We want the position. And that's the original minus 4.9, or it's actually right here, huh? Minus 4.9 t squared plus 30t plus 775. So, because that is the position. That tells you the position of the ball at any time. Well, we're going to take this time. We're going to plug it in, plug it in, plug in. T is, oops, 3.061, because that'll tell us the position, the height at that time. I'm going to plug in 3.061. Just hit the buttons on your calculator, Desmos, and you'll get 820.918. So that's how many meters up the ball was at its highest point, right? So it started up there at 775 meters, but somebody threw it up and it went up even higher, went up to, what was it, 820, up to 820. That was the top after just past 3 seconds, and then it's going to come down to the ground. So there it is for that part. Now, what's the ball's velocity at the above height? Well, it's going to be zero. At that very top spot, the velocity is zero, right? It freezes in space for just a split second. 0 meters per second, because velocity is always meters per second, or it's a distance per unit time. The ball's acceleration, well, the acceleration is always negative 9.8. There's no t here. There's nothing to plug in. So you don't need to plug any time in or anything in. The acceleration is always just negative 9.8. So if they ask you acceleration at any time, it's always negative 9.8. What does that mean? That means the Earth is pulling down on that ball always with the same gravitational acceleration, pulling it down at 9.8, negative 9.8 meters per second squared all the time. Whether the ball's flying up or flying down, the Earth is always trying to pull it down, right? Even if the ball's sitting on a table, the Earth is trying to pull it down. The table's just pushing it back up so it stays still on the table unless it rolls to the edge, off the edge, then it'll be pulled down to the ground by the Earth, right? Earth is always pulling down on all of us all the time with an acceleration of negative 9.8 meters per second squared. So acceleration is just that. All right, there's more. But wait, there's more. It's like a great infomercial. It's not like that. All right, here we go. Determine the time required for the ball to reach ground level. All right, so when is the ball going to hit the ground? Well. That's not a nice question. Coming on down. It hits the ground when the S of t is zero, when the height is zero, right? So I got to go back and grab the S of t function, which is that one, minus 4.9, 30, and 775. So plus t equals zero, because this is the height. This is the height. It's the position, the height. So we know when's the position going to be zero? It hits the ground when the height is zero. So how do you solve that equation? Definitely need the quadratic formula, right? Quad time. So we're going to need to do the quad. So here we go. I'll write it out here real quick. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's plug it in. Here we go. So what's this A, B, and C? I think you know. This is A. Oops, there we go. A is the number in front of t squared. This is B. And this is C. So negative B plus or minus square root of B squared minus 4 times A times C all over 2A. What a mess, right? What a mess. So what are we going to do about that? We're going to go to Desmos because they just want a an answer with decimals. So I'm writing it down. I'm gonna go to Desmos. Okay, let's go to Desmos. So I go to Desmos here, and here we go. I'm going to hit the fraction button, type that in, negative 30. I'll just do the plus first. Plus the square root of 30 squared minus 4 times A, which was minus 4.9, times C, which was 775 minus 4AC all over 2A, which is again minus 4.9. Boom. There we go. I got minus 9.8888. Now that's one of our answers. Minus 9.8822. Let's go back. So this is t, because they were solving the variables t. Minus 9.88, I don't remember. 9.8822. Anyway, now I'm going to go, so it's 8822. I'm going to go up. I'm going to change this. Now watch, just go back and then erase that and make it minus. And boom, there's the other answer. 16.0047. 16.0047. This was 2. All right. So this one is negative. That is baloney. The only answer is this one. Yep, we got it. Rounds to 0.05. We got it. That's from the bulk trend. Now, what you might wonder, what's with the negative answer? Why did it give us a negative answer? Well, here's where you have to remember. Math is not real. Math is a made-up tool helping us to figure out things that are real. So let's go back to, let me show you the picture of the ball. So here's the ball that we threw, right? Um, right here. And we threw this ball right on that. So the program's not being very responsive. Um, so there's the ball, and okay. So we're going to throw it up and it comes down, right? And it comes down. Well, what the math did is the math just made this U shape go backwards in time and said, oh, it would have hit the ball back here at negative whatever time. Well, we know that the ball started here. It's not just a U shape that you can go forward and backwards, but math doesn't know that. Math just took the U shape equation and said, oh, it's going to hit back in time here and forward in time there. We just ignore the negative answer because it's not in the real world. You can't run that back in time. Whoops, I'm on the wrong part of the problem, huh? We're down here. So the real answer is 16. That's seconds. So the ball will hit the ground 16 seconds after being thrown off that building. Now, what's the velocity at that time? Well, you just go to the velocity equation now. So we go, okay, so to the velocity equation, which was the first derivative equation, which was negative 9.8 t plus 30. You can go back up and find it. And then just plug in. We're just going to say, okay, so what's S prime? We're just going to plug in now. That time, 16.0047. 16.0047. And when you hit the buttons on your calculator, you'll get a velocity negative 126 meters per second. It's going down awfully fast. All right, last question. And so you see what we did there. We just plugged into the velocity the time, because this tells you the velocity at any time. So if they want to know the velocity when the ball hits the ground, then you just plug in the time when the ball hits the ground right there. And you find the velocity at that time when the ball hits the ground. Final question, what's the acceleration at that time? Well, as we talked about, acceleration is always negative 9.8. So there we go.